In August 1977, the spacecraft Voyager 2 was launched from Cape Canaveral on its grand tour of the giant outer planets. Almost exactly 12 years later, it's come to its final rendezvous. On its way to Neptune, it's bypassed Jupiter, Saturn and Uranus, sending back new information and incredible pictures. And now, Neptune is within range. Before Voyager, we knew comparatively little about Neptune. For example, only 2 moons or satellites were known. But when still over 20 million miles and over 3 weeks away from closest encounter, Voyager discovered several more. The Jet Propulsion Laboratory in California is where the entire mission is controlled. And during the next few days, leading up to Voyager's closest encounter with Neptune, many more discoveries will certainly be made. Representatives of the media from all over the world will be gathered here. And the press room, now silent, quiet and deserted, is going to be the scene of furious activity. The project scientist is Dr. Edward Stone. Ed, how do you feel about having the attention of the world focused upon you yet again?
Well, we're already very excited about the encounter, and we're just very pleased that so many other people in the world will be able to share our excitement next week.
Well, Voyager's been a triumph so far. Are you looking forward to equal success with Neptune?
Well, I think we've already had more discoveries, pre-encounter discoveries at Neptune than I can recall we've had at any other planet. So yes, I think we will have many discoveries ahead of us.
Have you any worries? And I'm thinking of rings and ring arcs.
Well, actually, we've chosen our flyby so that we stay outside of the region where the ring arcs had been seen from Earth. And so far, the ring arcs we've discovered are indeed safely inside where we're flying through the ring plane.
With the Uranus pass, the highlight was undoubtedly Miranda. If you had to make a guess, what do you think is going to be the highlight with Neptune? Triton or Neptune itself?
Well, I think it will probably be Triton. I hope it's going to be Triton. It'll be the last object we'll visit on our way out of the solar system, so it would be very nice if indeed Triton were the highlight of the encounter.
Voyager 2 certainly hasn't been without its problems, but at the critical moments it's always functioned excellently. The project manager is Norman Haynes.
Well, the spacecraft is made up of many systems, power systems, systems for controlling the spacecraft attitude. One of the systems is the radio equipment, the transmitter for transmitting data to the Earth, and the system for receiving signals from the Earth. Shortly after launch, in the spring of 1978, the radio equipment, the receiving equipment, failed on Voyager 2. Fortunately, we have 2 of most of these systems, so we switched to the backup system, and it worked okay, but we discovered we also had a partial failure of the backup system. So since that time, we've been sending commands from the Earth to the spacecraft through a slightly injured single radio receiving set of equipment.
And yet it still worked perfectly. It's a most amazing spacecraft. Can you take us through the vital bits of it?
Yeah, the basic parts of the spacecraft are, first of all, the antenna and the radio system through which we transmit the signal to the Earth. Secondly, we have a power subsystem. It's a radioisotope thermal generator, it's called, an RTG for short. It's a small nuclear power source which develops a lot of heat due to the radioactive decay of plutonium, and that heat is converted into electricity, which operates the spacecraft. Also, on the other side of the spacecraft, on the other long boom, is a rotating turret or platform called the scan platform. On that platform are 5 remote sensing instruments, 2 television cameras, an ultraviolet spectrometer, an infrared spectrometer, and an instrument called a photopolarimeter, which makes very detailed visual observations. We also have 5 other instruments on the spacecraft, which measure various parts of the solar wind, which is blowing out from the sun, and the magnetic field, which fills up the solar system.
After leaving Saturn, there was trouble with the scan platform, but that's now been put right, hasn't it?
That's correct. Right at the end of the Saturn encounter sequence on Voyager 2, this platform, which moves in 2 degrees of freedom with the remote sensing instruments on it, froze in one axis, just stopped moving. The reason we believe we ran into a problem was we ran it at its maximum rate. At that rate, we run into the lubrication problem. So since that time, we've operated it only at its lowest rate, and at that rate, it works almost perfectly.
One thing that I do find amazing is that the spacecraft is actually more up-to-date now than it was when launched.
That's correct. We were fortunate, I think, in that this was the first spacecraft that we put computers in several of the major systems. Those computers allowed us to update the program, so to speak, to change our mind about the way we wanted the spacecraft to operate.
Now, looking ahead to Neptune, do you anticipate any problems of guidance or control?
Well, we believe that everything's working fine. We don't expect any problems. Communication-wise, we have added into the ground network, the receiving network for the signals, several new antennas this time, which has allowed us to return about the same number of pictures or data per day that we did at Uranus, even though we're much further away from the Earth.
And once past Neptune, Voyager 2 will go on into space. How long do you think you'll be able to stay in touch with it?
Right at the moment, we believe that as long as the spacecraft continues to operate properly and doesn't break, so to speak, that we should be able to receive a signal from it for at least 25 or 30 years.
The signals, travelling at the speed of light, 186,000 miles per second, take over 4 hours to reach the Earth. But remember, Voyager is nearly 3,000 million miles away. The signals from the spacecraft are almost unbelievably faint. The power used to transmit them wouldn't be enough to light up the bulb of an ordinary domestic torch for more than the tiniest fraction of a second. When the signals eventually reach Earth, they're sent from the ground stations to this building, the Deep Space Network. This is the nerve center of the entire operation. It sends and receives all the information to and from Voyager. It reminds me remarkably of a scene from a science fiction film. The raw data are then sent to the image processing laboratory.
Here is a typical raw image. It has the Rousseau marks that are put on the Vidicon faceplate for calibration purposes, and you can see very little. It's a low contrast image. What we do, particularly if we're going to make a color image, is we take 3 images taken through 3 separate filters. That is, a blue image that is taken through the blue filter, a green image, and a red or an orange image. Now, these are still not quite cleaned up and not processed, but we then increase the contrast, remove these calibration features, remove any other artifacts created by the camera itself, put them all together, and then that will give us a color image. And you see it going together, and there it is. That's Neptune, perhaps a little bluer than one might see it if they were riding on the spacecraft, but a pretty good representation of what you would see if you were on the spacecraft.
You very often use false color, not for publicity, but for scientific analysis.
Yes. Let me give you an example. There's just so much of a grayscale, the brightest whites to the blackest blacks that one can display on an image. By using color to represent intensity, and this is what we're doing right here, it gives us another dimension. In other words, it expands the dynamic range over which we can display data. Now, that's one reason that we use false color. There are other cases where it sort of represents just a shift of the visual spectrum from the region our eyes are sensitive to. For example, supposing we were making an image that contained an ultraviolet image, a blue image, and a green image. Now, our eyes are not sensitive to ultraviolet, of course. What we do is we make the ultraviolet blue, we make the blue green, and we make the green red, and that gives us a false color image of the planet, but it's telling us about what the ultraviolet light distribution is.
One problem that's going to affect you both at Neptune and, of course, with the satellites is the low light level. Is that causing serious problems?
Yes, it causes some problems. Because Neptune is 30 times the distance of the Earth from the Sun, that means that light levels are only about 1/900th of what they are here on Earth. And that means longer exposures. And the problem with longer exposures is that we have a camera system with a focal length of 1.5 meters, and with such a very long focal length, the spacecraft has to be very, very steady. Now, just small instabilities in the spacecraft or the motion of the spacecraft itself can tend to create blur. So what we have to do is find a compromise between exposure time and the strength of the signal, and then on top of that try to make some corrections for the blur. But we think we can do it, and in spite of these low light levels, we're getting very good photographs.
Quite apart from the 2 cameras, there are 10 other experiments on Voyager 2. Many of these are using a new system of data analysis, VANESSA, Voyager Neptune Encounter Science Support Activity. This means the data can be shown clearly in real time, that's to say, just over 4 hours after being transmitted from Voyager 2 at Neptune.
The really main advantage is speed. In prior encounters with planets, we've had to usually wait for several hours at least before a tape was handed to us, which we then had to mount on computers before we could even begin to analyze it. With VANESSA, which we have here, we can see in real time the data as they come down from the spacecraft within seconds they are plotted up here on a screen for us to look at.
Well, I know you're concerned particularly with the radio emissions from Neptune, and they have been detected now.
That's right. We detected radio emissions about 24 hours ago. We're seeing the data coming down from the experiment.
So they're actually coming down straight at this moment
That's
from
right.
Neptune, 3,000 billion miles away. What exactly is that screen showing us?
Okay, what this screen is showing us is time is along this axis. On this axis, vertically, we see the radio frequency spectrum, which is covered by the Planetary Radio Astronomy experiment. The experiment covers frequencies from 1.2 kilohertz down here at the bottom, all the way up to 40 megahertz here at the top. Many of these periodic features that we're seeing are interference that we detect from other instruments on board the spacecraft, but these few spots around here, those are Neptunian radio emissions.
Are they like those of the other giant planets?
In the main, no. They're quite different from the emissions at Jupiter and Saturn. Uranus had a little bit of everything, and these are fairly similar to some of the ones that we saw at Uranus. They tend to be very intense and bursty emissions.
What do you know yet about the magnetic field of Neptune?
Well, the prime thing we know is that it exists, which we didn't know 24 hours ago. This is the first detection ever of a magnetic field at Neptune.
The first official press conference was held 4 days before closest approach. Voyager was still more than 3 million miles away from Neptune, but already a tremendous amount of information was coming through. The first and most important thing is that the images are every bit as good as we'd hoped, and the entire scene is dominated by the Great Dark Spot.
Certainly this is a marvellous encounter, and the Great Dark Spot is a great surprise. We had no idea just how active Neptune was going to be, and what we have found is an incredibly active weather system on this planet. A huge feature is about an Earth diameter in size. In fact, in size in proportion to the planet, it's rather like the Great Red Spot was on Jupiter.
It's not the only dark spot.
No, in fact, we've seen a second picture which shows, in fact, how we've seen some other dark spots, and also it shows when you compare the one at the more southerly latitude towards the pole, it's moving at the greater speed, and look very carefully in the inside of it, Patrick, you'll find a very bright white area as well.
And in the Great Dark Spot itself, there are obvious changes over short periods.
Well, I think there's a spectacular sequence we've seen already, and quite honestly, we don't understand half these things. We're seeing long white streaks, cirrus-like clouds, then suddenly this tail produces a whole stream of tiny little dark eddies, little sort of vortices coming out of it.
Triton's going to be fascinating, but already we can see some detail on the surface.
Well, Triton is going to be a spectacular, slightly smaller than we thought. It's now about sort of 1,400 kilometers in radius. So, and also the other thing is it's very bright and very cold. Now, even at the resolution we have at the moment, we can see that there are different sort of colorations on it, some bright white areas and darker features as well.
3 days before closest approach, Voyager is still 2,300,000 miles from Neptune. And at this morning's press conference, there was a most surprising announcement.
Is that the inner arc, the one that we were unable to find since the Discovery images, is there. It is just outside the orbit of N3, and it is continuous. Neptune's first complete ring.
Gary, did that surprise you?
I think it surprised everybody, Patrick, more than we expected. And furthermore, it's incredibly faint, therefore very difficult to find, and yet another amazing Voyager discovery.
We also had another magnificent picture of the Great Dark Spot, a false color picture, but very striking.
We're seeing a lot more detail in the features. You can see the Great Dark Spot, wispy, very high cirrus clouds. They're probably frozen methane or some other substance, but you can see a lot of banding, so the motions themselves are definitely zonal, like we'd seen on the other planets.
Now, too, we're starting to get clearer pictures of the surface of Triton.
Well, Triton itself is looking very, very exciting. With every passing second, of course, the resolution goes up, but that we've seen so far, this coloured picture is showing a lot of variation across the surface. Up towards the northern part of the satellite, we see a well-defined sort of band.
2 days to go before closest approach, and Voyager's closing in on Neptune. Distance now, 1,380,000 miles, and we're getting even better pictures of the Great Dark Spot.
Well, in fact, when you look at this picture, Patrick, it looks as if material is flowing down into the Great Dark Spot. And in fact, it's slightly an illusion. Look at it very carefully, and what actually you can see are the wispy white clouds very high up, like a cirrus cloud. And the darker material may be sort of H2S, hydrogen sulfide. If you had this situation on Jupiter, then you couldn't get these high cirrus clouds actually condensing, because it wouldn't be cold enough.
What more have we learnt about the rings and the ring arcs?
Well, certainly I think we're beginning to understand a little more of the observations that were taken from the Earth and be able to compare those with Voyager. There were about 6 arcs thought to be observed from the Earth, but now we've looked at those observations made from Voyager. There are definitely 2 systems around Neptune that Voyager has seen, and certainly one looks definitely continuous, and another which we may also think is continuous.
And what about Triton? There are certain areas that appear to be blue.
Yes, we do seem to have found the first bluish tinge on an object since we left the Earth when Voyager started. That bluishness, which we can actually see in the coloured image, possibly could be caused by the radial scattering effect, the same effect that gives us the blue sky. It may not be molecules necessarily causing that, because very tiny particles, and they could be scattered around in the lower part of the atmosphere. But Triton is looking really fascinating.
We are now only a day from closest approach, and at the moment, Voyager is less than 500,000 miles away from Neptune, and every hour seems to bring its quota of new discoveries.
We have 2 new satellites, and here they are. This is the planet, 1989 N5 and 1989 N6.
They're very small objects. One's 50 kilometres, the other's 90 kilometres in radius. So they're small objects, very distant. In fact, little streaks is all you can see at the moment, because they're part of very long exposure images to actually find them.
And I'm also intrigued by the fact that the cirrus clouds above the great dark spot appear to be so high above the general cloud deck.
Well, in fact, this rather colourful picture is taken a couple of methane images, put one into the blue filter, one into the orange, and put them together. And a very bright area, which looks rather like space shuttle from the sort of orientation you look at it, is in fact part of a very high cloud that goes around the great dark spot at 23 degrees south. Now, what appears white are in fact very, very high clouds. They are above the major cloud systems. They're methane ice, extremely high in the atmosphere. And what we are lucky, and what indeed we have made a major breakthrough on Neptune, we're now for the first time learning something about the structure of the clouds. In fact, this next picture shows us shadows on the major diffuse cloud system of Neptune. The sun will actually be in the sort of the top left-hand corner, shining down across the image. So in fact, you can see that one side of those streaks is bright, the other side is dark. And we've made some very preliminary calculations to suggest that the tops of these very strong storm clouds may be as high as 50 or even 70 kilometres above the hydrogen sulfide clouds below. So Voyager's found shadows in the atmosphere of a major planet. We haven't seen them at Jupiter or Saturn or Uranus. Another major discovery.
At this moment, Voyager 2 is at its closest to Neptune, skimming over the North Pole at only 3,000 miles. And you can just imagine the atmosphere here in the press room at JPL.
Probably the last time in our lifetime.
Even tiny debris could destroy Voyager.
5 hours after the closest approach to Neptune came the closest approach to Triton. And all through the night, together with other television crews from all over the world, we've been watching the pictures of Triton coming down from the spacecraft. And amazing pictures they are.
I think at the moment it's a tremendous chance to celebrate a successful flyby of Neptune, a flyby now of Triton. The pictures we are seeing are just amazing. They're so stunning, we're having great difficulty, in fact, in explaining them at all.
In point of fact, though, there seem there to be features that look rather like faults.
Well, what you would get on this sort of surface, which is a little bit icy, is perhaps sort of compressional activity, setting up stresses, and then, yes, perhaps faults, plates, material buckling, giving the small undulations that we actually can see. This is where literally X marks the spot. You can see an enormous cross of 2 very long features, suggestions of craters. I'm not really sure if they are, but certainly some way the material sort of stacks up and forms a very complicated domain. After X, of course, in the alphabet, here is the Y that we're searching for, and you can see it towards the top of the picture. But my goodness, Patrick, what a strong difference in the surface to the left and to the right, a very strong boundary, an indication, yes, of the way the surface has changed and been modified, perhaps by the material flowing out from the polar regions.
I realise that Triton's atmosphere is very thin, but do you think it has any effect upon the surface as it is now?
Well, it may actually help as a shield against some of the charged particles. It may actually affect some of the radiation actually reaching the surface. So the surface chemistry may be controlled a little, even by this little thin atmosphere that we have. And you can see in this last picture a well-defined haze a few kilometers above the surface. Now, what we're trying to understand is whether we actually have a haze which is photochemical or other material that's composed in it. They're the sort of things that we're searching for.
One day beyond closest approach, and already Voyager is more than 1 million miles beyond Neptune. At today's press conference, there was another very interesting revelation.
Okay, now for a quiz. How many rings can you count in this picture?
Let's see if we can work it out, because it certainly is quite complicated. Look very carefully. Let's start with the easy parts. Here is clearly one ring, and here is a second. If you look very carefully through here, there's another one showing up quite plainly. And then, when you look between this particular region, there is certainly evidence of one ring and a separate part, making the total of 5. But what's more important is, in fact, that there's enough diffuse material around, so the rings actually have materials spilling out, in fact, even connecting them together.
The one thing we missed out on this time was Nereid, the satellite with a very eccentric orbit, because Voyager didn't go anywhere near it.
Well, the image you can see here is the best one we're ever going to get. So this image just suggests it's there. We're not going to know very much. It's quite dark, has an albedo of about 10%.
Well, let's go back now to Neptune itself, and what I think is the loveliest picture so far taken.
Well, aesthetically, absolutely beautiful. Let me explain what it means. This, in fact, is the beautiful high clouds above the rest of the sea of Neptune beneath it. And it's from images like this that we've been able to work out precisely how high those clouds are above the main cloud decks. We're wrestling with the exact numbers. It could be as high as 70 kilometers, and we're talking at huge methane clouds. They're part of sort of convective systems as well that are penetrating high throughout the main weather atmospheric part of Neptune.
Today, we haven't heard so much about Triton, but one very interesting thing came out of the press conference, and that was concerning Triton's atmosphere.
Well, of course, we found a third object now in the solar system with a nitrogen atmosphere. We're not sure yet how thick the atmosphere is. We know we can see the surface, so it's not a massive atmosphere, but certainly a nitrogen atmosphere. That's important to us particularly because nitrogen at these very cold temperatures can exist in 2 states. One in the atmosphere and another through the sublimation state. It can appear in the solid mode on the surface, and that may help to vary some of the surface features.
Voyager 2 carries instruments of many kinds. Of special interest is Neptune's magnetic field. We'd assumed it existed. It was confirmed only about 30 hours before closest approach by the plasma wave experiment when Voyager 2 passed through the bow shock. And so far as we can tell, the magnetic field is about the same strength as our own. Then there is infrared. Dr. Dale Cruikshank is a long-standing member of the infrared investigation team. Dale, what has infrared told us about Neptune's internal heat?
The internal heat source on Neptune was found from ground-based infrared observations. In fact, Dr. David Morrison and I were among the first to make such observations at Mauna Kea in Hawaii in the mid-70s. And it was clear immediately that Neptune was warmer than it should be for its great distance from the sun.
Why is it?
Well, I wish I knew the answer. What I can tell you is that both Jupiter and Saturn do have excess heat coming from their interiors, presumably as a result of the phase changes of the chemicals within them, whereas Uranus does not. And that itself is quite a surprise. Now we're back at Neptune, another planet that has an internal heat source, and by having a third example of those planets which do, we have a better chance of identifying the causes.
I know that Triton is one of your particular interests. What's the surface really like? Is it nitrogen ice or methane ice, or what is it?
The coating on the surface of Triton is a subject of very great interest and one that we're still puzzling over at the present time. What we do see from both the pictures and from other measurements is that we have a snowy, frosty surface covering most of Triton.
A flight of fancy. Imagine you're standing on Triton and looking around you. What will you see?
I think you see a dazzlingly bright surface around you. Dazzling even though the sun is so much further away than it is from us here on the Earth. A surface that you could kick, for example, and expect to see a little flurry of flakes of frost and snow push out ahead of your foot. You would see vast expanses of flatness. There's relatively little topography on Triton. There is some, but relatively little. You would see very little in the way of local craters of the kind that we find, let's say, on Mars and on the Moon. A very icy, a very polar, a very frigid place that one might best find an analogy for in the Antarctic regions on the Earth.
2 days beyond closest approach, with Voyager now more than 2.25 million miles beyond Neptune, and a most surprising suggestion that there could be activity on Triton now.
We now believe it could be seeing geysers, Patrick, and I think that's a great surprise to us all. Look at this picture, you can see the sort of dark streaks across it. Now, the first thought is, a little bit of atmosphere. Could there be some wind? Is it wind-blown material? No, we don't think it's that. But the idea of this being continuous just shows you that there is active geology of sorts taking place on this very distant object.
Then there are these strange formations that we call frozen lakes.
In fact, the best place to start, Patrick, is that crater that sits in the middle of that very smooth lake area. Look very carefully. You can see one side is white, the other side is dark. It actually is the shadow, so the sun is coming from the left. And if you look across there, you can actually see that the land rises and falls very, very slightly. And probably what is going on is that there were lakes, they freeze, the material drops a little, refreezes again.
But we do also get small craters.
That's actually quite interesting. These craters are in fact very, very, very small. If you look very carefully at this picture, you can see a large number of craters which may be no more than a few kilometers across.
You know, Triton has really been the highlight and has tended to divert attention from Neptune.
But I think the important news from Neptune now is, yes, at last we know how long the day is on Neptune. It's 16 hours and 3 minutes. So that's helped us to pin down some of the wind speeds. And the fastest wind speeds we've found, which have been features like the Great Dark Spot, about 300 meters per second.
3 days past closest approach, and already Voyager is more than 3 million miles beyond Neptune. Here at JPL, scientists are starting to make serious evaluations of the results of the mission. It's only a few weeks since we were really wondering whether we'd be able to see through the thick clouds in Triton's atmosphere. And we now know that Triton's atmosphere is extremely thin, with a ground pressure of less than 1/100 of a millibar, so it couldn't possibly contain clouds of that nature.
No, in fact, I think this is a very important result. Also, the surface temperature is quite cold. It's 37 degrees Kelvin, about the sort of temperature we expected. But here, Triton's atmosphere is very thin, mainly a nitrogen atmosphere, but it does have, obviously, a certain amount of methane involved. But the important thing is that's the reason we've been able to see the surface quite so effectively.
They're also lovely pictures. What about that polar view of Neptune?
I think that's particularly exciting. When you look at that picture and towards the left-hand bottom of it, you can see that bright cloud for which we did see those shadows and detected, in fact, that the clouds were about 70 kilometers above the diffuse blue clouds beneath. But also look very carefully, you can just see the polar vortex.
The satellite N1 was discovered only during Voyager's approach. It was a great feat to photograph it.
Well, I think that there's no doubt, having seen it during the approach to Neptune and then to actually get these remarkable pictures, and you can see in this picture that it's highly irregular in shape. You can see a very, very large crater-like feature on the surface, but also, Patrick, it's extremely dark. We've got used to the very bright aspects of Triton. Here is an object which actually, if you could pick it up in your hand, will be as dark as the soot you would find in a chimney. It is extremely dark, reflecting no more than perhaps 2% at best of the sunlight incident on it.
And of course it's outside the main ring system.
Yes, the rings themselves really are amazing. This particular picture of the rings is a triumph for engineering. This is a 10-minute exposure. Just think of the long exposures one takes with one's camera and the camera shake we get. You see the two well-defined rings, and inside the brightest ring you can certainly see a third, and that's reasonably quite broad. But what is particularly interesting is from the innermost ring, which is about 45,000 kilometers away from Neptune, there may be material extending all the way down to the cloud tops.
4 days after closest encounter, and Voyager is now more than 4 million miles beyond Neptune. At today's conference, we saw a video of a trip over Triton.
think an example not only of the performance of the spacecraft, but also what's been done with the processing on the ground, because a tremendous amount of work with the amazing modern computers have transformed our views of Triton, give us a chance to look at it.
And now that the encounter is over, what are your final thoughts?
I think when I go back to Triton itself, I think Triton must clearly be the most exciting object we've actually thought about and discovered the most amazingly varied surface. Also, I think very recently that we've now got the idea that the density on Triton is now more than 2 grams per cubic centimetre. And that's important because it's much heavier than the icy satellites that we've seen during the Voyager mission. And it may help to actually give some clues to the actual origin of Triton. When we took a very long exposure picture, Patrick, Neptune cast a shadow right the way through the rings. It actually gave us some indication for the first time of a lot of continuous material. But inside, you can actually see where the shadow bites into the diffuse material, and you can see a lot of very tiny particles which make the ring seem continuous within the rings themselves. We've now had this amazing flyby of Neptune. Now, as we leave the planet, we're looking back to see the crescent of Neptune, the crescent of Triton II. This is a very fitting farewell for Voyager to leave the Neptune system.
Dr. Edward Stone has been project scientist all through Voyager, who's seen the entire program through. Ed, now that Neptune's been left behind, what are your general impressions of the Neptune encounter?
Well, I think it's been remarkably successful. We discovered a magnetic field, which we expected to find, but unexpectedly it was tilted 50 degrees with respect to the rotation axis, much like Uranus, and that was a big surprise. We thought Uranus was peculiar because Uranus itself is tipped on its side. Turns out that Neptune has exactly the same kind of peculiar magnetic field. Of course, once we have a magnetic field, we have radio emission, which comes out periodically, and that allowed us to measure the length of the day on Neptune for the first time, and it's 16 hours and 3 minutes. Then, of course, we expected to find ring arcs. We actually found complete rings, 3 complete rings with a broad distribution of ring material between them. The weather system was a big surprise. We didn't expect the planet, which has only about 5% as much energy to drive the winds, to have 750 mile per hour winds as we found on Neptune. We also discovered 6 small moons, and again there was a surprise. One of those small moons is not so small. It's as large as the moon Miranda in orbit around Uranus. And finally, of course, there's Triton. We expected to be surprised by a moon which has methane ice and possibly nitrogen ice. We discovered that there is indeed nitrogen and methane in the atmosphere. It's mainly nitrogen. It's 37 degrees Kelvin, that is almost 400 degrees below 0 Fahrenheit, the coldest surface we've seen on Voyager anywhere in the solar system.
It's fair to say that with Neptune, everything went according to plan.
Essentially, everything went according to plan. We had actually asked the spacecraft to operate at peak performance, and it did.
So Voyager 2 is on its way, with Neptune far behind. Its story is not over. It should remain in touch for the next quarter of a century, by which time it will have reached the edge of that part of the galaxy where the sun's influence is dominant. After that, who knows? It could even end up in some alien museum. But of one thing I'm certain, Voyager 2, the most successful of all unmanned spacecraft, will never be forgotten. From the Jet Propulsion Laboratory in California, good night.